No, hopefully not. Okay. So I did my presentation, sorry, I'm doing my project on 2011 PHM Society Conference Data Challenge. So I'm going to talk about what the challenge is. I'm going to talk about the issue of icing. I'm going to talk about my unsuccessful shear algorithm and now my current shear algorithm. I'm going to talk about my planned improvements for the shear algorithm, and finally I'm going to talk about my pair algorithm. So the conference, the challenge is they give you this set of data from these wind sensors, and they want you to determine when the wind sensors have error. And an error occurs when it's 2% off from the actual wind speed reading. And there are two types of setups. One is pair, where you have two wind sensors that are at the same altitude, and the other type of error is other type of set of data is shear, where you have three sensors that are at different altitudes, or you have four sensors that are at different altitudes. For the shear data, which is what I'm going to refer to it from now on, they want you to determine whether there's an error at all in any of them. And for the pair data, you have to determine which one's an error, or if both are an error, or if neither are an error. So in the shear data, just to give you an idea, this is the data we have. We have seven training sets, 25 days each, and it's training in the sense that there are no errors in this data except for icing. So you can use this to identify where icing has occurred, and then as you can see how much test data we have. In each file, we have the altitude, we have the wind speed, wind direction, temperature, and date. For wind speed, wind direction, and temperature, they give you four statistics: mean, min, max, and standard deviation. And also, these statistics are gathered every 10 minutes. And in the pair data, you have the same similar quantity, close to similar quantity of training and test data, and the same types of statistics, except you don't have date. So I'm just going to talk about icing. All the algorithms that I'm going to discuss later, I already sort of filter out icing, so that's a given. So I'm just going to explain a little bit about that. So this is from a test file, which means that it's there's no sensor error. And by the way, I forgot to say, icing is not considered an error. And so this is the mean wind speed. And as you can see here, these two, this is with so this was with four sensors. These two have icing. And it's icing because the standard deviation is 0, so essentially the sensor is frozen solid. It's a rotating sensor. So basically what I do is to identify icing, I identify regions that look like this. I say any sensor readings around here, even though they're not frozen solid, they can still be slowed down from ice that's accumulated. And also I add a buffer to the end, and if there was more room over here, I would add another buffer there saying those are icing conditions. And so we're going to discount that because if it's stopped right here, then it's probably also kind of slow here with accumulated ice. So the first method dealing with the shear is I said, well, wait a minute here, isn't there a wind gradient? So if I know the wind speed at one height, I should also know the wind speed at the other height, and if it's not that, then I know one of the sensors is an error. And so I found this equation, and this is often used, the Hellman equation is often used, sorry, let me go over it. You have two velocities, typically the way it's used is you want to determine the wind resource of an area. So you have the wind speed where your sensor was located, the altitude, and then you have another altitude that you're going to put your wind turbine at, and you want to know the wind speed there. And in that situation, you actually know the Hellman exponent. But with the shear data, they give you the wind speeds and the heights. So actually, I calculate the Hellman exponent. And so if the Hellman exponent is, since there's a wind gradient, since all the sensors are at one position, even though there are different altitudes, they should have the same Hellman exponent. And so if there are different Hellman exponents, then that means there's an error. So it actually turns out this doesn't work. And the reason it doesn't work is because it's too low. The altitudes are too low, and this is actually, there's too much interference. So for example, you should never, the highest, it's the Hellman exponents you saw previously is usually between 0, almost never 0, 0, and the peak is like 0.7. And so when I first got these, and actually you can see here it's negative, which means it's actually faster at lower altitudes than higher altitudes. And at first when I got this, it was like, oh, there's some bug in my code. And eventually I looked through it and there wasn't a bug, and I actually selected pieces of data and looked at it. And in fact, I knew that there would be exceptions to the equation I showed previously, but I didn't know that the exceptions would be the rule. And so this isn't a method I can use. But I wanted to talk about what I did. So the next method I decided to do was a shear aberrant method, or SAM. And so there are basically three steps. The first step is identify features. Well, identify features, and I figure out how to weight those features, and I use simulated annealing to weight those features. So, for example, in the shear data, a feature might be you're measuring the you're looking at the wind speed, but you could also look at other things, like you could look at the difference in wind speed between two different altitudes, because even though I talked about before there being not really a consistent wind gradient, there still could be a relationship at a certain period of time between the wind speeds at different altitudes. And then using those weights, I find a threshold for error, and finally I apply that. So when we're talking about the distance between measurements, basically the idea is that you're looking at your current measurement, and the assumption is that that's based off of your previous measurement, and that if it's not closely related, if the distance is far, then the sensor probably has an error. So I use simulated annealing to, and the idea is that if you're looking at different features, I select a bunch of features, and some of the features might not actually be useful. Some of the features, so for example, wind direction might not be a very useful feature, and so that means that wind direction is going to change a lot in the training data, and then that means it's not useful, right? And so what I do is I use simulated annealing to find the weights for the features that minimize the total distance, and so therefore the features with the highest weights are the most relevant. So basically, I'm minimizing this function. Given I'm iterating through and trying to find the optimal feature weight. That's what I use simulated annealing for. And I take the dot product of the feature weights and the features. So and then finally, I apply that threshold. And basically, the way that works is so you saw those. I'll go back. I see somebody's confused. So basically, when I'm doing this, I'm actually doing this on the test data. Sorry, on the training data, and then I run that through on the training data, the feature weights that minimize the distance, and then I find the mean distance, and then I'd go, I look at I find one standard deviation away, and then I go through the test data, and I find any data that's beyond any file that goes beyond that, and by that I mean it's has more values outside of standard deviation than it should, then I know that's an error. So one obvious way to refine this would be to expand the feature set, and that's not very hard to do. Something that's a little more slightly harder to do, but something I think is probably more beneficial than expanding the feature set at this point, is actually segmenting the. I'm assuming like the training data and the test data are all the same, are in the same type of environment, but that might not actually be the case. And so it could actually I could segment the training data into different sort of weather areas, and the same way with the test data. So the pair, which I spent less time on than the shear, so just to refresh you, the pair is where they're at the same altitude, and where you're trying to determine not whether there's an error, but in any of them, but which one has an error, or if both have an error, or if neither have an error. So the assumptions is that the wind is the same at both sensors, which may not actually be completely true because they're at the same altitude, but they're 20 feet away from each other because they're each on a 10-foot outrigger. And another assumption is that wind sensor failure slows down the sensor, and well, you can read the rest. So this is just to give you an idea of a typical measurement, and here this is from the training data, and you can see the icing, but just to give you an idea of what it looks like. So going on. So the pair algorithm, this was pretty simple. Basically, what I did is as I said, since they're about the same area, the speed is not going to be exactly the same. But if one is consistently slower than the other one, then that's probably an error. And so what I did is I looked at the training data and figured out what that threshold is, and then I applied that to the test data. Although actually I did the pair data first, but I discussed shear first because in fact I want you to understand how shear works, because I'm actually going to apply that. I'm going to generalize that method, and I'm going to apply it to pair. And so that's what I'm working on now, because I'm going to have to look at different features, because instead of just deciding whether there's an error, I have to figure out which one has an error. So that makes this a little bit more complicated. Any questions? I have a question. How much time did I take?
10 minutes.
Okay.
Yes.
Yes?
Did they get back to you about your submission?
Ah, yes. So I had some issues registering. So I finished registering like yesterday. It's kind of confusing. And so now I haven't actually submitted it yet, but I will probably like submit something and have like a result back by Monday, 12 p.m. Sorry, 12 noon. I forget if that's 8 p.m. Any other questions?
How many submissions can you do?
Oh, you can do one a day.
Order?
Yeah, yeah.
So you're going to take your 3-step methodology and apply it to the pair data?
Yeah, actually, I should be done with that this week. Like, that should be in my Monday submission. Yeah, that isn't too hard to do, actually. So, but after that's done, I'm not sure really what I'm going to do next. Any questions? Any confusion? Okay, thank you.
Well,
yes?
Question. So, how many faults have you identified in your current setup, like in share and pair data?
Oh, well, I had a graph. I don't remember off the top of my head.
Roughly, like you identified
Oh,
like
it's
50%.
Yeah, it seemed like it's 50% probably.
That's a lot.
Yeah, I'd expect that there would be a lot of errors in there, but I don't know. We'll have to see. So, and also it's a 2% error, so any like slight problem in my code or something I missed can throw off the results. So there'll probably be some refining. So I think refining can really make a big difference in the results.
So you said the maximum error can be 2%.
Maximum error. Or any, I mean, no, not maximum error. I mean, anything below 2% is not considered an error.
Oh, okay.
Yeah.
Yeah, so I meant, yeah.
Okay, thank you.